So the next speaker is not available online yet. So we'll move on to the fourth talk, which is now the third talk, by Guido Martínez from Microsoft Research. And he'll talk about the next frontier for AI-generated kernel correctness.
All right. Can you folks hear me okay? Yes. All right. Hi, thank you for coming. So yeah, I'm going to tell you about correctness and AI-generated kernels. So I suppose everyone here has heard about GPUs. GPUs are running the planet these days. They're running all of our agents and doing all of our experiments. And they're very hard to program. They are essentially a coprocessor to the CPU. They have a different memory. They have a very parallel structure. They have different memory hierarchies. They have complex synchronization. In GPU kernels, you also need to think about optimized math and memory transfers, and things are really complicated. And when you make a mistake, like an indexing error or you have a data race, you can start getting wrong answers. Your kernels can be non-deterministic, and it's a really difficult place to work on and debug. At the same time, there's a lot of interest in agentic programming of kernels, as for many other fields. So to gauge whether agents and LLMs are able to generate GPU kernels, recently there was there's a set of challenges called KernelBench. It's about 250 PyTorch functions that you have to implement in CUDA, and they're a way of measuring whether a coding agent can actually come up with CUDA implementations of these operations and how fast they can make them. So the game is to make them as efficient as possible. That is the cute logo from KernelBench. And current models like Opus 4.6 or whatever, or 8, now pass KernelBench easily. They can code up all of the challenges, at least to get a passing solution, and then they can make them more and more efficient. At the time of the publication of KernelBench last year, this was not the case. NVIDIA, after a couple of months after the paper was published, I think, NVIDIA reported that they could pass level 1 very, very easily. But what about correctness? So people are generating these kernels and they're measuring them and trying to make them faster. But we feel the attention has been mostly on the performance of the kernels, and correctness has gotten comparatively little attention. The correctness bar for these kernels is usually the same. You test them with a bunch of random inputs, and you accept them as good if they match some reference implementation on these random inputs and within some tolerance, because there's floating point everywhere in these kernels. And you could say, this is usually testing cannot guarantee correctness, of course, but you could say these kernels are usually kind of regular. Is testing enough? So the first claim we're making here is that tests are not sufficient, and we find several failures in the KernelBench test suite. So we find buggy kernels that pass the test, correct kernels that do not pass it, and also just cheats that you can completely sidestep the challenge. So as one illustrative example of a buggy kernel passing, one of the challenges is implementing a softmax function. And it turns out it's only tested on one input on a very large matrix that has about 400,000 columns, so the rows are very large. And by doing some mutation testing of correct solutions, we found racy kernels passing this benchmark. So you just remove barriers, and your kernel is obviously incorrect if you think about it, but it still passes the test. You can skip some of the outputs. You can just not write them. You can write everything a bit too far, and you can even actually just memset it to 0 in this case and still pass the test. So this was a surprising example. And it turns out that just this test is particularly bad because the rows are so large that the denominator, and that's the definition of softmax, the denominator is so large and the numerator is so small that these are very, very close to 0, way below the tolerance. So it's like, this test is just really bad. And then, adding more randomization helps, but it's difficult to think that you would completely get rid of these things. We've also found correct kernels that fail when they happen to be adding things in some different summation order from the reference implementation. So there's a challenge number 4 in this test suite is a matrix vector multiplication, which you can also think is just a matrix multiplication. And if you just take the textbook implementation of like the naive mathematical definition and you run it, you get a failure that says you're off by 50, but you're off by 50 from the actual result. And it turns out that torch.matmul, which is the reference, just uses a different order. And then if you change this textbook definition to do some something called a KN compensated sum, a technique that reduces error, then you pass. But this is really the same algorithm mathematically. It's just one of them is, you were just far from the spec. And in this case, you could say that the spec is actually doing the better thing, and that is the thing you should compare against. But we found other cases in level 2, actually, in some more complex examples, where a better algorithm with less numerical error fails the test because the reference is just bad. So in a way, you're just comparing two floating point numbers, and you don't really have an idea of which one is the right one. Even more problems is just reward hacking. This is reported even by the KernelBench authors that the LLMs are just trying to make you happy and trying to pass the test, and they can completely sidestep the challenge of whatever you're asking them to do. So for instance, this setting the output to 0 can pass softmax. And it's also a question of how much you trust your LLMs, because you would have to review all of the code to make sure that they're not doing anything like this. They can definitely insert, if you don't trust them, they could insert a Trojan that you will never catch with testing. And other things that the KernelBench authors have found is that, well, you ask the thing to do a CUDA implementation, well, it doesn't do that. It just calls PyTorch, which is the reference, so it obviously passes, but it's obviously not the challenge. There's some funny mistakes also, like just a kernel that does nothing happens to have uninitialized memory that matches the reference run, so that also works. But it's pretty difficult to defend against all of these things. And we don't think that testing is the right way to do it. So what is the right way to do it? Our proposal here in this paper is that we can have AI-generated, AI-verified GPU kernels that come with a proof of correctness once and for all, and you don't need to test them. So we propose to verify things statically over the whole input space. You don't need to have test many distributions or whatever. And we're thinking about memory safety, data race freedom, and functional correctness. And then the trust, the thing that the human has to review instead of the entire code and the dependency graph, is just the specification. That is basically the source of trust. To do this, we propose using Kuiper. Kuiper is a verified GPU framework built on FStar and Pulse. It gives you memory safety and data race freedom as table stakes. You cannot write unsafe kernels in this language. And it also allows you to state and verify precise functional correctness. And then Kuiper code extracts to plain CUDA, and then you just compile them as usual with NVCC and you run them. And it's also highly reusable. You can define highly reusable kernels and kernel components. There's a high degree of polymorphism. And if you want to learn more about Kuiper, the paper is in this PLDI, so you can come to our talk on Wednesday about it. I won't say much about the language itself, actually, but what I will say is the high degree of polymorphism is important. So just to give you a taste, this is a slightly shortened implementation of a gem in Kuiper, but it has very precise pre and post conditions and invariants and etc. And if you look closely, this is, well, actually, never mind. But you can write this over any type, so polymorphically over any type, or polymorphically over any layouts, and polymorphic over any operations that you want to do. So you verify this thing once, and you can extract just plain usual CUDA code that does the matmul, but you can also extract many more variants, but you only pay for the verification once. So we're going to make this verified language the target of the generation to solve the challenges, or to get your kernels. Compared to other approaches like Proofwrite, which is also recent and also targeted KernelBench, we're not trying to verify random or generated CUDA code at the level of CUDA. We're verifying something higher level and then generating the thing that we want. So then we check everything before the CUDA even shows up. The CUDA does not exist if the thing is not verified. So to do this, we just set a swarm of agents to go through the entire level 1 of KernelBench, like 100 challenges, and read the implementations, understand them, and write a Kuiper kernel that implements that. To begin with, so usually verifying is more complicated than just writing a kernel. You need to think about the invariants, you need to think about precise pre and post conditions, you need to call the relevant lemmas to help the prover discover what you want to prove. So to make this process a bit more efficient, we split this into two tasks, two phases. The first phase is to implement a Kuiper kernel for the thing we want to do, but without really verifying anything. Just basically, the only thing you're proving is that it's memory safe and data erase free, and it generates some executable CUDA code. And then we run this against the KernelBench framework to see if it actually passes the test. Once we have this, which is like a relatively quick signal and it's relatively cheap, then we can think about verifying. And in the first stage, the agent is allowed to admit proofs that it thinks are hard for the moment, and then just test it to see if we're on the right track. And then when we have confidence that we're on the right track, the phase 2 goes to like do write a fully precise functional spec for what you're doing, add the invariants, add the ghost code, add the lemmas, and iterate until you have a fully verified working kernel. And in this, here's also a place where it's important that the language is constraining what you can do. And whenever you're about to do something that is unsafe, the verifier will say, no, this line I cannot prove that it's safe, so you should go and fix it. And the agent can go and loop and spell out the proof in more detail. So with this framework and using Claude Opus 4.6, we've obtained solutions for all of level 1 of KernelBench that pass the test suite. They are all verified in Kuiper, and they have fully precise specs, like the spec guarantees that they're implementing the mathematical operation that they claim to be implementing. And 100% of the code is verified GPU. There is no unverified CUDA in the mix. There is a slight amount of unverified CPU code to just like bridge between the testing framework and the CUDA, and the verified CUDA coming from Kuiper. And this was written almost entirely by LLM agents. So this is very feasible. Like we did not need, with the current capabilities of LLMs, we did not need like a complicated setup. This was basically one Copilot session, very, very long Copilot session, but it was one session where we just talked to it. The human, in a way, was just architect, reviewer. We decided if things looked good enough to take. We also, one important thing that we had to do is tell the model to reuse previous results and follow a consistent style instead of just basically biving it, and use the polymorphism that you have to make reusable components, which otherwise it did not do on its own. And here the language was very important, actually. There's a big set of challenges where they all follow the same structure in this level 1 of KernelBench. There is a map that takes two matrices and overwrites the first matrix with some combination of the first one and the second. Then there's a reduction, usually by rows. Maybe you add all the rows, and maybe first you square them or something to compute like mean square error or something like this. And then there's a small final post-processing that you do maybe per element or maybe on one final result. And one of the advantages of doing this in Kuiper is that each of these stages is a super generic, highly polymorphic function that you can just call, and then you can just reuse. So each of these things took some effort, especially the tree reduction, which Jonas over there was the original author of. But once you have this, and once they're genetic enough, you can just compose them very, very easily. Some of the challenges are around 60 lines of pulse code, which is really not much at all. So yeah, the per kernel work, the per challenge work is relatively small. The heavy lifting is in this shared library of general combinators that you can use. And some of these existed before we attempted this, but some of them were added during this work by prompting the agents to do so. One thing I should say, since I was speaking about floating point, is that Kuiper allows you to verify floating point in some approximate notion. So it's really difficult to give concrete error bounds. So what Kuiper is doing is giving you this idealized relation between floating points and real numbers, and you prove things via this relation. So for instance, when we talk about a parallel reduction, like adding all of the elements of a row of a matrix, the post-condition you get is that the result is a correct approximation of all of the sums of the matrix. And this could be in any order, this could be in any associativity, be in any commutativity as well. So for instance, the challenge I mentioned that was fixed by the k-n summation, both the failing one and the passing one have the same spec. So the spec is approximate in the sense that it does not really, we do not and cannot really prove concrete error bounds, but it gives you a spec that is very, very composable. So for this particular issue here, one has to keep in mind that a fully precise spec does not really tell you much about the concrete error bounds. But what you can do is you prove this precise approximate functional spec, and then you go and check numerical error, go and call your oracle. And if that fails, you see how you can fix this kernel to keep the specification but be numerically better. So what was harder in this? A couple lessons we learned. So reward hacking is still possible, even though we are checking that they're not admitting proofs or something. It has happened that when they cannot prove something in Kuiper, the agent will just go like, oh, I'll just write a CUDA wrapper for it, and it just defeats the complete purpose of the experiment. But with some review and some also like very explicit indications to the agents, this was minimized. Also, that the library was the cause, not each kernel. These genetic combinators were really what made this possible. And also that some obligations that were really structural and tedious, they resisted automation. They were very difficult for the agents to perform. But thankfully, most of these are very low stakes or something we could fix manually after. So just to conclude, testing cannot certify kernels. We don't think this is a very viable way of certifying. Proofs are now practical, like all of this, 100 different challenges, which is mostly completely automatically performed. We think the languages are key. Like this is only possible because the language is giving me all the guarantees, and I only have to review a small bit of the spec. When I see the agent does something funny that I don't like, I can go and say, hey, go and refactor it, and then if it does and the specification is preserved, then I'm happy enough. I don't need to review every line of code. So trust mostly to the spec. So things we want to work on next is in making these things more performant, making the agents more reliable, and better at writing code without many iterations, and intern formalization, by which I mean giving you a way of reviewing the spec in a principled way. So that's all. Thank you so much.
Thank you. How did you teach the agent the Kuiper language?
Oh, they learned it. So I think they have some knowledge of F-star because F-star has been public for a while. So Kuiper is built on F-star, and there's the pulse separation logic on top of F-star, which is relatively recent. F-star has a long history, like 15 years maybe, though it's changed. So I think they have significant knowledge of F-star, somewhat less knowledge of pulse, and basically no knowledge of Kuiper because this was not even public at the time. But they can infer what they have to do. So
you did not even give any reference documents about the language. This was just the verifier feedback. Agent learned to write Kuiper.
I think examples and verifier feedback. I don't know. They're so autonomous that I don't actually know what they did. They could have pulled the FSTAR and Pulse book. There is a book online posted. I suppose it's in the training set. Some version of this book is in the training set. But as far as Kuiper goes, I just told they figured out they're in a repo and they look at examples, and verified feedback is super important. And the fact that they can grab and find to see what they can do. Yeah.
Sorry.
Hi, Shipadi Pai, University of Rochester. I know performance is your next goal, but I was just curious, what is the performance of your current L1 kernels compared to maybe the best?
Yeah, we haven't measured much of these actually. We were just concerned about correctness. I think they're not doing a lot of all of the fanciness and the optimization techniques are baked into the combinators, which some of these existed before. So I suppose some of these are relatively performant. Like there is a tensor core gem implementation that is using some challenges. This is relatively performant. It's in some GPUs it's competitive with kubeless, and the softmax implementation I think is also relatively performant. But I don't have numbers I can show you. Yeah, sorry.
I have questions about the trust you give to the spec.
Yeah.
So first, what are the size of the specs for these challenges? And also, do you have examples of situations where the agent did something wrong with the spec? What kind of bad things did you
Yeah, I have a couple. I think the rough size of a spec is, well, they usually look very similar in like, there's a function with a bunch of parameters, and it says, if I have all these conditions on the input, then there's this condition on the output. And that condition, then you need to see how it's defined. I would say usually it's between 20 and 30 lines. Maybe a bit more. Well, if you count the dependency cone. That's also the thing. For instance, one of the first challenges is a batched matrix multiplication, which means I give you an array of matrices and another array of matrices, and you give me an array of the products one by one. And then the first thing the agent wrote was, oh, I'm going to take an array of b times n times k and an array of b times k times n, and the result is this thing. And it just defined the product again, basically, which the product for matrices of 2 dimensions already existed, but the one for 3 did not. So in that case, it was like 100 lines, and I couldn't make sense of it. So my indication there was like, no, do not do this. Go and use the spec from here, and this is the way this should look. And then when you do that, it's really small. It's like this matrix 3, on every index, it's the product of the other 2 matrices. And that I can understand, it's like 2 lines. Then about hacking, one thing I did find is that sometimes the post condition would just be true. They say, oh yeah, whatever, this is future work or something, and they make some comment about it, and they just leave it like unimplemented. Yeah, so those 2 things happened, I think. I should say reuse is important not only to get the kernels, but spec reuse is also important so I can understand it, because I know a bunch of components, and if they reuse it, that's easier. Yeah.
Hi, Sangeeta Chaudhary from AMD Research. Very cool talk and very cool work. So how scalable is this approach? So maybe it might work for kernels, small kernels like GEMS and GEMP, but nowadays trend is towards mega kernel where entire forward pass is fused into one kernel. So how do you see applying this approach to mega kernels?
Yeah, I'm not sure a completely autonomous approach would work to do like a super performant state-of-the-art kernel. But I think generating the components, so we can generate components in a way also that they sometimes can be fused. So if you just generate a wide array of components and you have some algorithm in design that is just fusing some parts, I think the agent could very well put them together. But we haven't reached here. In a way, the point of this paper was also to, well, figure out if this is possible at all. I suspect it's not true that the agents will just like knock it out of the park for like state-of-the-art kernels, at least today.
Very nice talk, Guido. Yeah. So I've been trying to understand bugs that have been reported in the PyTorch repository. And for anyone interested, I have a catalog of 90 bugs and so on. I've been trying to work on them. And we also have built a binary instrumentation tool in our group just to look for NAND bugs, because these are some of the most widely reported. Mm-hmm. It's very eye-opening to actually see an LLM in action, so you can actually prompt a bioimage trial or anything, produces pretty good answers for whatever diseases you utter. But inside, it generates 100 billion NANDs. So there, you can see actually in the code base X not equal to X in many cases, and we know why it does. It actually traps NANDs and then resets it to convenient values. So I don't know what the logic that these kernel writers follow in handling NANDs, except they do. Otherwise, the outputs will be corrupted. Mm-hmm. So I suspected, my suspicion is that kernels are not very composable. You might verify kernels for specific input ranges, but there is no guarantee that when you compose them, these ranges won't be blown. So they had to fix the NANDs. So I suspect this is a point of action for the community, for people assembled here, saying how can we really make this composable, and specifically also build a good set of tools like you are building to inject these kernels back into PyTorch and see. Yeah, that's a meta comment.
So I totally agree. Yeah. I totally agree, and that's these specs about floating point that we provide, that they're approximate, but the point is that they're composable. That's why I like them, because I can compose them. But they don't catch against NANDs. Yeah. This spec does not guarantee that something did not become a NAND or an INF. We cannot do that without bounding ranges and doing other reasoning. I would say that's probably better for like a second passive verification, but I don't know yet.
Yeah, anyone interested, write to me, ganeshutah@gmail.com. Yeah, I can send you what I collected. Yeah.
Hey, thank you for the talk. So the spec that you're using, it must be written by human experts, right?
No, they're also written by agents, but we review it.
Okay. I recently read a paper where the authors were mentioning that the agent did the right thing, but the spec was incorrect, and they were updating the spec based on the agent traces. So I want to know, in your experience, did you come up with did you encounter such scenarios where you termed that the spec was correct, but then later you realized because the agent gave you the...
I think given this two-phase thing that we were doing, that's unlikely. Like, the agent comes up with a spec after it knows that it passes the KernelBench suite, which is not a big guarantee of anything, but at least you know that it's not completely broken. I don't think I found any wrong specs, actually, the fact that they're actually wrong. What I did find is that they're written in a style that I don't like, or they're like not reusing things that I would like them to reuse, or they're like 100 lines longer and then I can't review them. This I did find, but actually incorrect I don't think I found. Yeah.
Thank you for your talk. I had one question. Do you also formalize do you use inline PTX in your kernels?
No. Yeah, we don't have that yet.
And you cannot support it because you cannot provide the specification?
I don't know if we cannot support it, but today Kuiper does not allow it. I think maybe something you can definitely do is probably, if we extend it, add inline PTX and just assume that this thing has a spec. So it becomes something you trust, but at least you could do it. Then formalizing PTX and their semantics, I don't know if this is tractable at all. But if it's even well understood, I think probably not. Yeah.
Thanks for the talk. So I have one question over the kind of the polymorphic aspect of the element type. So I see you have array 2 and the element type may be a shape. So how does that? So how do you handle different floating point data types? Like, would the same thing works for FP32 also work for like BF16, FP8, and that kind of thing? And in order to understand like how good your modeling of the floating point error is, have you tried like removing the part where you run the KernelBench correctness test, but directly go to verification and see what's the proportion of things that you can verify, but actually fails the floating point test?
Right. I think you had two questions. So one is, yes, we can do any of these types. And as far as the real reasoning go, they're all equivalent pretty much. You just get that, basically, if I have that A approximates real A and B approximates real B, then the sum at whatever width approximates the real sum. And this is what you get. And there is no notion at all of error. So all of these algorithms, numerically, they could all be way off. There's no numerical, I should say maybe there's no numerical guarantees. So then about if they pass, what can you verify it pass and not pass the test? I think if you do softmax, but you do not normalize by subtracting the max, this will definitely pass in Kuiper. Because subtracting the max in the reals is like a no-up. It doesn't do anything. But numerically, it will explode. So that would be one example. I didn't run the agents on this loop, but I'm sure they will find such examples, yes.
Okay, yeah. Let's thank the speaker for answering all the questions and for the amazing talk.
Thank you.